disable breakpoints. You want to be careful with that. It's DISAS. And then lists will list will list 10 lines of source code from your current line. So if you want to see like where in your C function you are, then you can do list. One thing to note is like you can't really use list for bomb lab because we aren't supposed to be seeing the C code, and that might explode your bomb. So although list is very useful, I don't think you guys will be allowed to use it for bomb lab, but you can definitely use disassemble. That is key. So yeah, that's just a little note there. So like, as I mentioned, breakpoints are spots in your program where you'll continue execution until you reach a breakpoint. And there's several ways to define a breakpoint. You can say break and then your function name. If you also know the address of where you want to break at in your assembly code, you could do break star and then the address. Info B will show you the current breakpoints that you have and then the numbers, and then you can disable specific breakpoints with IDs. You could also just disable all of them with D or like the DIS, and then you can clear breakpoints as well. As I mentioned, watch points are places that, again, your line of execution in your code will stop when the specified variables change. And by similar logic, you can delete watch points, you can add watch points, you can see what watch points you have. And yeah, here are examples. So like if you wanted to set a watch point for a specific variable, you could do like watch and then the variable name. Or if you want to watch like for a numerically entered if you want to watch for a change in a numerically entered address, you can do it by dereferencing that address and then calling watch on that. So yeah, I think that's it for the watch points. And then I think the last thing in terms of GDB commands is printing. So printing is super useful. So printing and inspecting. So printing is super useful because you can print the value of variables. You can also print the value of registers, print value of data structures, values of pointers, and so forth. So that's a super useful command, and it's going to be super useful in these next two labs and malloc, and other labs where you're going to need to use GDB as a debugging tool. And so is inspecting memory. So inspecting memory, like if you have a specific address or a specific register, like a common thing is you'll want to inspect the stack, right? So we know we have RSP as our register stack pointer, right? So if we wanted to inspect the stack, we know we would start at RSP, and then we would want to inspect a certain number of bytes past RSP. So I'll show an example of this in a second, but those two commands are super useful in just inspecting what is going on with your registers, values, variables, so forth. Yeah. Oh yeah, and then so one of the last things I wanted to talk about is backtrace. So backtrace will wherever you are in your line of execution, if you do backtrace, it'll show all the steps that it took to get to where you are. So if you look at this example, right, and it prints it out backwards. So we start at main, then we went to printf, and then we keep moving up the chain of calls, right? And that's what backtrace does. It tells you, well, I am in this function in a certain line, which was called by a different function, which was called by a different function, which was called by main. So backtrace literally lets you trace your steps back in terms of function calls and everything. So that's also super useful when you run into issues, because you want to know like how you got to a certain function and yeah, and all that good stuff. So, and then the last two commands, up n and down n, so they allow you to go up n function calls, go down n function calls. So if you're at a certain point in your code, and it's pretty self-explanatory, right? If you wanted to go back to function calls, you would use up n and then down n for the other way around. And then you can also use call and then whatever valid expression if you want to call a function. So in your assembly code, if you see a function name you can try calling that function with a specific parameter in GDB, and it'll print out that value. So let's say you had factorial, you can do like call fact1, and that'll print fact1. And then by similar logic, you can set variables. So if you wanted to change the value of a variable in your C program, you can do that using this GDB command. And like this will allow you to step through your GDB code, changing parameters to functions, so you don't have to rerun your code. You can just be like, oh, what happens with this function if I pass in 3 instead of 2? Yeah, so that's pretty much it for the GDB commands. Yeah, so before we do the lab, I wanted to show you guys just a little bit of a just like a walkthrough of the some GDB commands that we were talking about. So as I mentioned, when you run, like when you compile your code, you will have it to have an executable to run GDB. So like I got logged out, so let me log back in. But I have my executable practice. So I wanted to show you guys just some C code in actually let me just print it out here. Right. So this is just a simple C function that has add, has multiply, has just some arithmetic function name, and in main, we're just calling arithmetic with 2 arguments, 5 and 10. So we have our executable for practice. So then if we do GDB, you could do \practice, or you could also just do practice. Both will work the same. And then if we run, nothing should happen. But if we wanted to analyze main, right? So here, right, we can see already, like we can see that the call to arithmetic matches up, right? So in this C code, we have the call to arithmetic with 5 and 10. And in this line, we call arithmetic. And then I don't know if you guys have gone over this yet, but RDI is the register that is associated with the first function argument, and RSI is the register associated with the second function argument. So already we can see that we have RDI, we're passing in 5 into the first function argument, and we're passing in A, which is 10, to the second function argument. So this matches up really nicely. And then we call arithmetic once we pass in those arguments. So we can set a breakpoint at arithmetic, if I can spell right. If we run, then we are in arithmetic, right? So this is the assembly code for arithmetic. So the point of this isn't for you to see like, oh, I'm, it's not for you to have to walk through this assembly code to figure out what it's doing. I just want to show you guys some like nice and useful GDB commands. So, you're kind of more comfortable with seeing what kind of everything does. So so right now, this little arrow is nice because it tells me where in my assembly code I am. So if I wanted to move forth, I can do next instruction, and it'll just move down an instruction, and I can keep doing that. And so, yeah, it's moving again. Add has 2 function. Add has 2 function arguments, so it looks like here it's moving those into RSI and RDI. Let me try list. So here we can see where we are in our code. Again, you can't do this in Bomber or Attack Lab, but just for these purposes, it's nice to see where we are. This will be super helpful in malloc as well. And then, yeah, we can just continue. And then here is an example of what the difference between next and step does. So instead of NI, which is next instruction, I'm going to do SI. So what this does is this now gets me in the assembly code of add, right? Before, when I was in here, if I were to do NI, it wouldn't get me into the assembly code. It would get me to this line of assembly code. Sorry, it wouldn't get me into the, it wouldn't step me into add. It would just move me to the next line of assembly code versus SI got me into the function add. And then we can set a breakpoint. Actually, let me show you how to set a breakpoint for an address. So we can set a breakpoint at the address right after the call to add in arithmetic. And then again, info B will show us, oh, right, we have our breakpoints. And then if we continue, we should continue until we hit this second breakpoint in arithmetic. Let's confirm we did that, and we did that, right? So yeah, we can analyze some register values. So if we analyze RSI, right, it's 10, which makes sense because our second function argument is 10. If we analyze RDI, it should be 5 because our first function argument was 5. If we analyze RAX, right, this makes sense because in our add function, we're just adding X and Y and we're returning that, right? So the return register stores the return value for the function that was most recently called. So here, when we're on this line of assembly code, the function that was most recently called was add. So the return value is going to be stored in RAX, right? We added 10 and 5, so it makes sense why RAX should be 15 because that is the return value of X plus Y. So that's kind of nice that that checks out. And then we can also print, if we wanted to print like the hex version, we can do p/x. And then we could also, if we want to see the stack, we can print, or we can examine the stack. So we can examine, let's say 10 bytes from the stack. If we want to see 72 bytes from the top of the stack. So again, PRSP is printing where RSP is pointing to, which is this hex number right here, 5F8. So as we see here, right, we still have the top of, like the stack is pointing to this slot right here. And then there's all these slots following this, which represent the stack growing, right? So that's gonna be super useful in like bomb and attack lab to analyze the stack. Yeah, and I think that's pretty much all I wanted to show you guys. But yeah, there's a lot of like neat things that you will learn over time with GDB. Yeah, well, all the commands, like I mentioned, it just takes practice and experience. But yeah, if you have any questions, definitely ask on Piazza or come to office hours because this stuff can be very new. Definitely start early on Bomb Lab so you can get a hang of things. But yeah, I think now is gonna be the activity. So the handout should be on the slides and we'll walk through the activity.
Yeah, so for some reason you want to disable a breakpoint, you can do disable 1, which is the breakpoint at main, and that'll disable that command. If you want to enable the breakpoint again, you can just re-enable it. So we're going to go ahead and run, right, so we broke at main here. Next, twice. This takes us to string copy, the second line in main. And then after that, we'll do secret message. This command right here is printing secret message as a word T, which if you look at the file, it's like a struct that contains a string and the length of the string. And so you can see if you print this, it'll print all those fields nice and clearly. And then next, yes. Printing this again, you can see that it's changed after unscramble into this weird little string here. And so we'll enter unscramble like so. And so step here, we're going to use step instead of next. And like Nelly said, for the most part, they're the same instruction, except for when you're about to enter a function. If you want to skip over like computation of this function unscramble, for example, then you would do next. And it would evaluate unscramble and move on to the next line in main. Whereas if you wanted to enter unscramble to see what's going on inside there, then you would do step. And step takes you into unscramble and then does next. So we're going to go into unscramble here. So right now we're inside unscramble, and you can disassemble if you want to see all the nice assembly here. And then next 2 more times, right? Right, so again, we could print the result of function calls, and as long as the function doesn't have any side effects, this is perfectly fine to do. So it can say, you can see that letter is in fact not alpha. We want to print letter, we can see that it's an exclamation point. And so we continue beyond this, step into reverse and backtrace. Oops. And so you can see where exactly we are right now. So we are at this libc-calc function, which is called by reverse, which was called by main. So that's really all there is to that first phase. Any questions? Awesome. And then for phase 2, oops. So this is trying to, there's a bug somewhere in this code and we want to find the bug using GDB. So normally you'd have to, in order to find bugs, you have to like litter your code with print statements, stop it like, every function, check to see what's going wrong. But this is a really easy way of finding out, especially like in big code bases, exactly where your program crashed. So you sort of let it crash first, and then from there, do backtrace to see like the stack of functions that led you to the point of error. So if we run here, we can see that we got a sig FPE, which is pretty vague. So to find out exactly what's going on, well, this already tells us a lot, right? If we see that return something divided by something, arithmetic exception, right? It's probably some sort of floating point error. So if we do backtrace, we can see that main called calc average, which is where this function is. So if we do list, we can look at the function, or we can look all the code in here and sort of start to get an idea of the environment that we're in at the moment when the crash happened. So this is the line in question. We have some sort of thing going on here. And so if you look at this code, you can probably start to see that we probably had some divide by 0 error right here. And in this case is a pretty small function, it's a pretty small file, so it wouldn't be that hard to find the bug. But as soon as you start working with like huge code bases, 1,000 line plus, this is a really good way to track down errors super quickly.